Okay, so it's my pleasure to introduce Alexey Pokrovskiy, who is now a lecturer at UCL in London, and who is a great expert in extremal combinatorics and probabilistic combinatorics. And he was a recipient of European Prize in Combinatorics 2 years ago. So thanks, Alyosha, for agreeing to talk on our seminar, and please welcome.
Thanks, Andrei. Thanks for the invitation, and Yo for coming. I'll have the chat open, so feel free to ask questions during the talk there. So this will be about joint work with David Correia and Benny Sudakov about rainbow matchings in edge-colored graphs. So it'll be a talk about edge-colored graphs, like these ones drawn here. And at a high level, it's about an interaction between two different kinds of colorings, proper edge colorings and rainbow colorings. So proper edge coloring is like this complete bipartite graph on the top. It's proper if at every vertex you don't repeat colors. A rainbow edge coloring is a kind of a trivial coloring. It's just one where all of the edges of the graph have different colors. And the basic question is, inside a properly edge colored graph, what kind of rainbow subgraphs can you find? So of course, you'll find a rainbow star at every vertex. That's just a definition of a proper edge coloring, but you'll also find some other rainbow subgraphs. So for the talk, we'll be looking for rainbow matchings in properly edge colored graphs. And there'll be a big focus on complete bipartite graphs, which is this graph on the top, because there's an old conjecture of Reiser, Beraldi, and Stein from the 70s, which says that essentially in every properly edge colored complete bipartite graph, you can find a nearly spanning rainbow matching. So you can find a rainbow matching which only misses one of the possible edges. So this will be a motivation for the talk. So the new results I'll present a bit later on will be about a generalization of this conjecture by Aharoni and Berger. But for now, for maybe the first half hour or so, I'll just tell you about the background of this conjecture, about the known results, and even prove some of the old results about this conjecture. So first, why is it an interesting conjecture? So there's one interesting feature it has is that coming out of this -1 term. So it's not guaranteeing a spanning rainbow matching, but just one edge short of spanning. And the basic reason for that is there are some constructions which don't have a spanning rainbow matching. So the simplest one is this coloring of K22. So it doesn't have a rainbow matching which uses both blue and green, but it's not the only example. And we don't really have a very good understanding about when this -1 term is needed and when it's not needed. So in a lot of colorings, you can get a spanning rainbow matching, but for some, you don't. Okay, so that's one reason it's an interesting conjecture. It's kind of got a strange behavior with the extremal examples. Another reason is it's got a lot of equivalent formulations. So these proper edge colorings of a complete bipartite graph, they're completely equivalent to some other important structures, namely lattice squares and particular hypergraphs. So lattice square is what's drawn here. It's an n by n array filled with, in this case, I filled it with colors with the property that you don't repeat colors in any row or column. And then another equivalent structure is a particular kind of 3 uniform hypergraph. So what I've drawn here is a 3 uniform hypergraph. So the parts are these. And so where was I? Yeah, so we're talking about these equivalent structures. So why are these hypergraphs equivalent to So what are these hypergraphs? So you have three parts in the hypergraph, and each edge has one vertex in each part. So for example, this is a 3 uniform edge. And the hypergraphs, they have a property that they're linear, meaning that through any two edges intersect exactly, or at most once. So you can only have these kinds of intersections between edges. So why are these three structures equivalent? So to see that, let's label the colored graph, the vertices 1, 2, 3 here, and A, B, C here. And then for the Latin square, if you label 1, 2, 3 for the rows and A, B, C for the columns, then like the ijth entry, so for example, this entry, it's the color it gets is the color of the edge joining A and 1. So that's how the Latin squares are equivalent to the colored graphs. For the hypergraphs, so if you label these three vertices 1, 2, 3, these three A, B, C, and you label the last three vertices based on the colors. So this one's red, this one's green, and the last one is blue. Then for any edge in the colored graph, so say, let's look at this red edge, the edge in the hypergraph that corresponds it will join 1, B, and the bottom vertex will be red because that edge is red. So that's how you get the hypergraph from the colored graph. So these three structures are completely equivalent, and you can phrase Rice's conjecture in terms of all three of them. So the Latin square one is not going to be very relevant for the talk, but the hypergraph will come up a little bit. So the hypergraph version of the conjecture is that under this assumption, you get a, so Rice conjectures that you get a hypergraph matching of size n-1. And to see that, you just notice that if you have three edges, say forming a rainbow matching in the color graph, say these three, then the edges in the colored graph that correspond to them. So the first edge corresponds to this one in the hypergraph. The second edge is this one in the hypergraph, and the third edge is this one. So they form a hypergraph matching. So this Rice's conjecture, it's related to the area of hypergraph matching, and it's quite an simple but unsolved problem in that area. Okay, so what's actually known about the conjecture? Most work towards it has been, so the conjecture asks for rainbow matching of size n-1, and the results have proved showed that there exist smaller matchings in the same setting. So here is all that's known about it. So it's a series of results always under this assumption, getting a matching which is smaller than n-1. So first there were two results where you have something that's substantially smaller than n. So Coxman and Drake found matchings of size 2/3 and 3/4 n respectively. And then there's a sequence of asymptotic results where each of these results finds a matching of size n-o of n for various values of o of n. So the first result here that was proved was independently by Woolbright and by Broud, De Vries, and Wieringa, with essentially the same proof. They showed a matching of size n-√n. Then there was a later result by Alon, Kim, and Spencer, which gave a slightly weaker bound, n-√n, with some log factors. And I'm only mentioning this because the proof method was completely different from the previous one. And then finally, there were two improvements of this √n, one by Hatami and Shor, who improved it to log squared n. So this was initially proved by Shor in the 80s, but Puya Hatami found a mistake in that proof, and then together they fixed the mistake and got a correct proof of n-log squared of n. And then recently, although it's not going to be the focus of the talk, but together with Kivesh, Sudakov, and Yepremian, we improved this log squared to log over log n, which is the best known bound. the next kind of really interesting thing to do would be to get n minus a constant, if anyone wants an open problem here. So another interesting thing about this problem is that some of the proof techniques that go into proving these asymptotic results have really very different flavor and very different generalizations when you try and generalize the techniques to other areas. So let me briefly talk about how all four of these asymptotic results are proved. So all four of these results prove the statement above, that you get a rainbow matching of n minus little o of n. The Woolbright argument, the flavor it has is the techniques is basically to, it's an alternating path approach. So by this, I mean, if you know the kind of the normal proof of the Koenig-Hall theorem, just for finding matchings in bipartite graphs, that's exactly what this Woolbright approach does, basically. And what does it use about the setting? So it doesn't really use that you're in a properly colored complete bipartite graph. What it really uses is that every color has lots of edges. That's the only feature that this proof uses. So if you have n colors in a properly colored K and N, then every color will have n edges. So that's every color has a lot of edges, and that's what this proof uses. The Lalonde, Kim, and Spencer is both a completely different approach and also uses very different feature of the coloring. So the approach, it's based on something called Rodal's nibble. I'm sure a lot of you have known about it, which is an example of a probabilistic method, something called the semi-random method. And what this proof basically uses is that the graph is regular. Meaning that every vertex is contained in the same number of edges, and also that every color comes up the same number of times. And this Lalonde, Kim, and Spencer result can be generalized in that direction, whereas the first result cannot. Finally, this Hatami-Shor result, I am not an expert on it, so I can't really say exactly how it works, but the approach basically studies 4 cycles which look like this, where say 2 of the edges have the same color, the other 2 might have different colors. And by switching along this 4 cycle, you can change the colors that appear on the matching. And so by studying these kinds of 4 cycles, they somehow get this n minus log squared of n result. And I'm not sure exactly what feature of the K and N this proof really uses, but it seems to use really that you are in a complete bipartite graph. Or at least there haven't been many generalizations of this Hatami-Shor result to graphs which are far from complete graphs. And finally, this last result with Kivesh and Yepremian, it's actually quite easy to summarize how the result works. It's a combination of these first 2 approaches. So it's a if you take the first 2 approaches, this semi-random method and this alternating path approach, and you put them together in the right way, you can improve the bound greatly. So if you kind of look at the bounds here, both of the alternating path approach and the semi-random approach give you a bound of roughly n minus root n. And you can kind of think of our approaches that when you put the 2 techniques together, the root ends cancel each other out and you just left with log factors. So that's a kind of vague way of thinking about it, but there is some truth to it. And what does it use about the properly colored complete bipartite graph? What it uses is more than either of the first 2 approaches. It uses some pseudo-randomness features of the complete bipartite graph. Okay, so that's the 4 proof techniques. I would like to, so what the talk will mostly be about is about this first technique and seeing how it generalizes. But before we get to that, I'd actually like to give you both of these proofs, particularly because they're, I think, important proofs for people who haven't seen them before. So let's look at that. I'll start with the Rodel-Nibble, the Alon-Kim-Spencer proof and briefly summarize it, just to show you the kind of direction in which it generalizes. So, well, let's look at the kind of proof sketch of the following theorem, which dates back to Pippinger, which says that every regular hypergraph has a nearly spanning perfect matching. So what the setting here, so Rice's conjecture would be is if you forget about this delta, if you have an n regular linear, so linear means, remember, any 2 edges intersect exactly or at most once, linear 3 uniform 3-parted hypergraph with parts of size n, then you can get a rainbow matching of size Rice would want n minus 1, and this Pippinger result will give you n minus epsilon n. And the way Pippinger generalizes the Rice conjecture is rather than just asking for the hypergraph to be n regular, the degree of every vertex can be whatever you want as long as they're all the same. So let's quickly look at a proof of this. So you could work as follows. So we're going to, inside this hypergraph, look at a subgraph of it randomly. So let's select every edge independently with probability epsilon over n. So with a very small probability, we get a subgraph, and we'll call this subgraph B, which stands for byte, which is coming from the technique of Rodel-Nibble. Let's work out the expectations of some properties that B has. So first, how many vertices does B have? So maybe just to give you a picture of how this looks. So through every vertex, you have a bunch of edges passing. And the number of edges through every vertex is exactly delta n. And what we're doing to get this subgraph B is just we select some of the edges independently with probability P. So let's count first how many vertices end up touching these edges of B. So the number of vertices will be the number of vertices of the whole graph, which is 3n, multiplied by the probability that any vertex touches the edge, which will be at most, let's see, epsilon over n times the degree of every vertex, which is delta times n. So you get from this, so this many vertices. Yes, so you get these n's cancel, and you get 3 epsilon delta n vertices that B has at most. The next thing we'll count is the number of vertices of degree 2. So that's vertices like this one, which touch 2 edges of B. And by the same argument as for on the first line, you get something like 3 epsilon squared multiplied by delta squared n. So this just comes from again, working on the probability that any vertex touches 2 of the highlighted edges, that delta n choose 2 choices for a pair of edges touching this vertex V. Both of those edges stay with probability epsilon squared over n squared. So next, let's count the number of edges that B has. So the number of edges will just be the total number of edges of the complete graph, which is delta n squared multiplied by the probability that each edge stays, which is epsilon over n, so which is epsilon delta times n. And finally, let's count the number of
and you want to, and you divide it by 3, right?
So this is just the number of edges.
Yeah,
so
yeah.
I think this is correct. So if you have
with parts of size and right?
Yeah.
Not the total number.
Yeah, so I think that's right. So the 3 is here basically.
And also Nina asked something in the chat.
Oh, sorry. I need to figure out how to get the chat to be visible.
I can read it.
Oh, yes, yeah, this should be. Yeah, I don't think I can see how to get this to appear. Yeah, so if questions come up, do tell me. I think. Yeah,
so I suppose, Nina, right? I suppose you mean just matching, not
rainbow.
Yeah,
exactly. Yeah, so I've deleted that there. Thanks, Nina. Where was I? So yeah, so just for the last step, so we've counted the number of edges of B. Next, we'll count the number of isolated edges. By this, I mean edges which don't touch any other edges of B. So basically, edges where all 3 of their vertices have degree 1 in B. And this will be at least the number of edges that B has minus like the number of degree 2 vertices. That will certainly be a lower bound. Okay, and now if you combine kind of the first and the last thing written here, you notice that B is essentially just a matching, because the number of vertices it has is 3n times epsilon delta, and the number of edges is very close to that over 3, or rather the number of isolated edges. So these 2 imply that B is essentially a matching. So we've basically picked out a matching. And then the very last observation for this is that I won't do this one carefully, but if you look at H and you delete the vertices of B, then this is regular, meaning that the expected degree of every vertex is the same. So you can calculate the expected degree exactly, and you'll get that it's roughly the same, that it's the same for every vertex. So now that's useful because it means that you can just repeat this process over and over again, deleting the subgraph B you find. So repeating this 1 over epsilon delta times gives a bunch of disjoint matchings. And they all will have this size. Something like this times delta n. And if you count the total number of edges, now you have this many matchings. They all have this size. If you multiply those 2 numbers together, you'll get this. So that I've skipped some details here. Mainly, I've only worked out expectations of quantities. Once you also need to show that things are concentrated and take care of the error terms there. But this is just the core of this result of Pippinger. So now let's look at a different proof of the asymptotic version of Rice's conjecture, which is this one approach of Woolbright and Brouwer, de Vries, and Wieringa, which uses alternating paths and similar to Hall's theorem. So what I'll actually prove is a slight strengthening of their method, which was found by Barat, Yarfash, and Sarkozy, and which is in a more general setting than just properly colored complete bipartite graphs. It's about properly colored graphs, which have lots of edges of every color. So the setting is you have n colors. Oh, sorry. You've got n colors. So for example, for n equals to 3, each color has n edges. So say you'd have one color could maybe look like this. But now you don't care how the actual colors look, so they can be disjoint. You can also have multiple edges. So something like this. And again, you're looking for rainbow matching of size, in this case, n minus root 10. So something like this is a rainbow matching. Okay, so that's the setting. Let's look at this proof. So it goes like this. Let's consider a maximum matching. So, or maximum rainbow matching. So let M be a maximum rainbow matching. So you just look at a biggest rainbow matching in the graph. If we're not done, of course, we can assume it has size less than n minus root n. So it's a bipartite graph. So there'll be two parts. Let's call them A and B. And let's call the vertices in A, which are outside of your matching. Let's call this A0. And then there'll be some colors which are outside of the matching. So let's give them a name as well. So the colors outside the matching, we'll call them C1, C2, up to. So how many colors will there be? If the matching has size less than n minus root 10, there'll be at least root 10 plus 1 colors there. Right, so next the proof will proceed. It will look a lot like a proof of Hall's theorem in that we'll look at the sets to which there is an alternating path starting from the set A0. That's one way of writing a proof of Hall's theorem. So to write the version we need here, let's define a collection of sets. So let's let AI be the set of all vertices in A to which there is a rainbow path from A0. I'll give a picture in a second. So a rainbow path which starts here and which is alternating. So, and whose edges alternate between M. So these black edges I've drawn. So this matching is M. And the missing colors. But I'm not going to look at all the missing colors. I'll just look at C1, C2, up to CI. So basically AI is the vertices to which you can get by an alternating path using the first I missing colors. So just to give an example, so there could be some edges here. Maybe this has color C1. This could have color maybe C3. And this could have color C5. Then this vertex would be in A1. This vertex would be in A3. This vertex would be in A5. And as a remark, we just immediately from this definition, we have that A1 is contained in A2, is contained in A3, and so on. So these are nested. Okay. So that's the definition. And we need to prove one thing about these sets. So the claim is that, so the sets are nested, so they get bigger. And the claim is that they get bigger quickly. So the size of AI plus 1 is at least the size of AI plus square root of n. And we'll see this will imply the theorem very immediately. Let's prove the claim first. So it goes like this. So each color has at most m minus ai edges touching m minus ai. So just as a picture, so ai is maybe this. The number of edges that touch this can be at most the size of this set. So that there's nothing in this statement. It just comes from the fact that you're properly colored. So you're properly colored. That means that every color forms a matching. So if you have any set of vertices, the number of edges in a color that touch that set of vertices can be at most the size of the set of vertices. So that's the first observation. So using that, you get that the number of edges which touch AI has at least, so we're counting now the number of edges touching AI. So how will we estimate this? So each color has n edges in total, right? And then let's delete these edges because they're not going to touch AI because they touch the other bit of the matching. So let's delete m minus AI. All of the remaining edges will touch AI. Oh, sorry, AI union A0. So we're counting the edges in the color touching this bit and this bit. And then this you can write as n minus the size of m plus the size of AI. And m, at the start, we know it has size at most n minus root n, so you get the size of AI plus root n. Okay, and so that's largely the end of the claim because
just a small question.
Yes. Sorry.
The alternating path here is so we always end with a black edge, right? So this is
yes,
what
we always end with the green because we're looking vertices inside A because of this bit.
Okay, so yeah, right. So all of that is just inside A. Yeah. Good.
Yeah. So basically, you get a bunch of edges touching this set, so that maybe they look like this. And the conclusion will be that each such edge gives a vertex of AI plus 1, which gives you this inequality that we're trying to get in this claim. So the way you see that is, so say this orange edges we're looking at, they certainly can't go outside of the matching because this way you'd get an augmenting path. So they have to go somewhere inside the matching, and therefore they all give you new alternating paths into A. Okay, so that proves the claim, and the claim implies the theorem because these sets get square root n bigger at each step, but there's also a trivial upper bound of n on the size of these sets because they all have to be contained inside the matching. So that's the end of this proof. So two remarks I want to make. One is that so I mentioned before that for this improved bound with Kivesh, Sudakov, or Yerperman, it's a compilation of the two approaches I've showed you. And I can actually explain now how this works. Basically, to get this improved bound, you first do this proof, and you get a matching, which has size n minus, let's say, epsilon n. And then you start doing this argument. And because you're starting this argument, not with just some arbitrary matching, but by this one, which came from this argument, it'll have some nice features which make this claim work better. So if the matching you started with came from here, then you'll be able to prove this claim with a factor of 2 here instead of a factor of plus root n. And that means that you'll get a contradiction much faster. So you'll get a contradiction in just logarithmically many steps. So you'll only need logarithmically many spare colors. So that's a kind of a better idea for where this.
Can you repeat this? Why do you get 2 there?
That takes proof. So but that's just what happens. So because that does take extra arguments.
Okay.
Yeah, so that was one remark for how this proof works. Another remark is just before we have a short break, because I think it would be quite interesting. So there's kind of 2 different ways of getting an asymptotic version for Rice's conjecture, and they have very different generalizations. So one which generalizes to regular hypergraphs, one which generalizes to colored multigraphs, and as far as I'm aware, neither method can prove the other generalization. So this alternating path argument cannot prove this theorem, and this random method cannot prove this theorem. So I think it will be quite interesting to generalize either method to prove the other theorem. So let's have a short break now. We finished by proving this result of Berger-Conjecture, which said that if you have a colored multigraph where every color appears at least n times, then you have a rainbow matching which uses almost every color. And the second half of this talk will be about what the right bound here is. And there's actually a conjecture about this, which strengthens the Rice's conjecture, which we started with, and it's a conjecture called the Aharoni-Berger Conjecture. It says that the setting is basically exactly what was in this Berger-Conjecture theorem on the previous slide. You have a colored multigraph with n colors. So something like, say if there's 3 colors, this could be 1 color, this could be another color, and wait, there should be 4 of each color. And the third color could be this. So every color has n plus 1 edges. So for n equals 3, there'd be 4 edges of every color. And you get a rainbow matching of size n, so rainbow matching which actually uses every single color. So in this case, it could be maybe this green edge, this orange edge, and this blue edge. So this actually does strengthen Rice's conjecture because, so in the Rice-Broyaldi-Stein conjecture, which was at the start, you have an n colored KNN. So if you start with that and you delete the color, what does that give you? This gives us a graph G with n minus 1 colors. And each color will appear n times. Just because in the original complete bipartite graph, every color had to appear n times. So this satisfies the assumption of this Aharoni-Berger conjecture. And so you get a rainbow matching of size this time n-1, so rainbow matching using every color, which is what Reiser-Buraldi-Stein actually wanted. So this conjecture is stronger than the Reiser-Buraldi-Stein conjecture. And this time there's kind of two asymptotic approaches to it. So there's two ways you can, before we were just looking for a rainbow matching, which is as big as possible. Here, there's two natural ways of weakening this conjecture to get some kind of asymptotic version of it. The first one is what we've already seen at the end of the first half. So this result of Barat-Giafra-Sarkozy, you can just look at use this assumption. So you have a colored multigraph, there's n+1 edges of every color, but try and get a weaker conclusion. So instead of getting a rainbow matching of size n, get a smaller rainbow matching. So weakening the conclusion. An alternative thing you could do is to get the same conclusion, which is a rainbow matching using every color, but have a stronger assumption. So with every n colors, you can have the colors bigger than n+1. So instead of having this n+1 here, you can put in like n plus little of n. And those are both interesting things to consider. So I'll refer to the first one here as the weak asymptotic version of the conjecture. And the second one as a strong asymptotic. The reason for the names is because the strong one implies the weak one. So let's look at that. So let's prove a proposition that the second statement here implies the first one. So how will this work? So we're trying to prove the weak asymptotics. So we start with a colored graph which satisfies the assumptions of this conjecture. So we have let G be properly colored with n colors and n+1 edges of each color. Let's delete some of the colors. So let's delete epsilon n colors, any of them. This will give us a new graph. A graph, let's call it G primed, which will have n primed, which will be the original number of colors, n+1 minus the number we deleted. And how many edges will each color have? So each will have initially they had, the number of colors will be n minus epsilon, and the number of edges each color will have will be still n+1, because that's how much you had at the start, which is equal to, or which is bigger than or equal to, n primed times 1 plus epsilon. So n+1, so that just coming out of this equation. Okay, so that means that if you look at this new graph G prime that we got, you can just apply this strong statement to it. So the strong asymptotic, if it was true, tells you that there is a rainbow matching using every color in G prime. so of size n primed. But n prime is n minus epsilon n, so that shows you that the weak asymptotic is true. So that shows you that this second statement, the strong asymptotic, it does imply the weak one, and also with the same error term. So if you have a little o of n error term here, then you get this statement with the same error term. And a kind of advertisement for where I'm going for this second bit of the talk is we'll eventually see that the converse statement is also basically true. So if you know this weak asymptotic version, then it also implies the stronger one, but the error terms will change there. So that's where we're going. But first, what's actually known about this conjecture? So we saw already how to prove this statement, the weak asymptotic. What about the strong one? The strong one took a lot longer to prove. So Berat-Gerfash and Sarkozy, this theorem was the weak asymptotic. So a rainbow matching of size n minus little o of n. For the strong asymptotic, it took a long sequence of papers to get there. So here is a sequence of papers where the assumption is you have a colored multigraph as before, n colors, and each color has this time substantially more than n edges. And the conclusion is always that there's a rainbow matching of size n or rainbow matching using every color. And there was a long sequence of results which reduced the number of colors you needed. So kind of starting with 7/4 n by Aharoni, Charbit, and Howard, getting to 3/2 n by Aharoni, Kotler, and Siv. And these last two results, they're actually asymptotic versions of the conjecture. So a couple of years ago, I proved the strong asymptotic version of the conjecture, and very recently with Correia and Sudakov, we improved it with a much better error term of n to 3/4. And also the proof of this last result is really short. It's actually the shortest proof out of all of these. So that's what I'll present next. So we'll be looking at this last result. So this is what I called the strong asymptotic before, with an explicit error term of n to the 3/4. So again, the setting is you have n colors. Every color has n plus n to the 3/4 edges, and we want to rainbow matching using every color. And the idea will be that we're going to black box this result of Berat-Gerfash and Sudakov. Yes.
Sorry, Alexey, just a small question. So for the weak version in this setting, what is, because maybe I missed it, but is it true that this Gerfash-Sarkozy result is the best that we know? So this
great question.
n minus square root n.
Great question. Yes, it's the best we know. So we don't know how to improve this root n.
So you haven't improved it in the meantime.
No, none of the. So I mentioned these 4 approaches to Rice's conjecture. None of them improve this. So
okay,
that's the best. This is the best we know.
Okay, thanks.
And in fact, none of them even match this. So this is the proof I showed you is the only approach to this weak asymptotic that I know of.
So no other result gives even n minus little o of n. No
as
other approach.
So yeah, like
okay.
if you could prove this using a nibble type approach, I'd be very interested.
Okay.
So let's look at this. So we're trying to prove this strong asymptotic version. So it's by something we call a sampling trick, which means we just pick a random set of vertices in this graph. So let's pick every vertex independently with probability. Let's say 2 over n to the 1/4. I think that'll work. To get a set of vertices. So to get a set S. So the picture is you have your graph and you pick some quite small set. So some small subset S. And let's figure out a couple of parameters of this set S in expectation again. The first parameter is how many edges are contained inside S. So let's count the expected number. And by count, I just mean lower bound, the expected number of edges where both endpoints are in S. So each color has, so how many edges inside S? So to count this, we know how many edges you have at the start, n plus 5 n to the 3/4. And the probability that an edge ends up in S is the probability that both of its endpoints end up in S, which is the probability that a vertex is in S 2 over n to the 1/4 squared by independence. And this, if you work it out, would be lower bounded by something like 2 root 10. Oh, sorry, 4 root 10. That's again a coarse bound. So this 2 squares into this 4, n to the 1/4 squares into a root 10 in the denominator, and then you're just using that this is at least n. That's how many edges are inside S. Now let's count the edges outside S. So the edges with both endpoints outside S. It's the same calculation, right? So this is inside S. For outside S, it'll be the same calculation. So it'll be this number, n plus 5, n to the 3/4. This time multiplied by 1 minus the probability squared. So 1 minus 2 over n to the 1/4 squared. And I'm going to need that this number is at least n. So this is number of edges outside S. So yeah, you can check this is at least n. So when you square it, you get something like 1 minus, what is it? 1 minus 2 over 1/4 or 4 over 1/4. And when you multiply them together, you get it that it's at least n. Okay, so both of these quantities are concentrated. So you can kind of assume that this is actually what happens for every color. So now you can just apply the Barat-Gyarfas-Sarkozy result. To the graph of things outside of S. So to these edges. Because outside of S, you have n colors and they all appear n times, which was the assumption there. So what does that tell us? It gives us some rainbow matching of size n minus root 10 outside of S. So here, let's look at that theorem again. So here's the Barat-Gyarfas-Sarkozy result. It's exactly the assumption that we need, right? And colors and edges of every color, you get a rainbow matching of size n minus root 10. So all we need to get a matching using every color is to find the edges in the remaining root 10 colors, and you can just do that inside of S because each edge has lots of edges there, or each color has lots of edges there. So then to finish it, you can greedily pick disjoint edges of the remaining root 10 colors inside S. And by this, I mean, you like pick one edge, then look at the next color you need, pick an edge in that color disjoint from the one you picked, and you keep doing this. Because you're doing all of this inside S, the matching you got here doesn't matter. And because you have 4 root 10 choices for every edge, because that's the number of colors, edges that each color has inside S, and you're only looking for root 10 edges, you always have freedom to pick each edge disjointly from the previous ones. So that's the whole argument. It implies this theorem. I think it's a bit embarrassing that we didn't notice it before, so that somehow through all this, there was also always this short argument sitting there.
Alexey, just another
Yes.
short question. So this 3/4. So where does it come from? I guess you need some kind of union, like things holding simultaneously, not an expectation.
Yeah,
so,
I think for this it's just for this, right? Or wait, am I wrong somewhere?
No. For this, you don't need this extra 5.
Oh yeah, you're right.
And to the
That's
3/4. It should be for the next, I think.
Yeah, probably for this one, right? And,
yeah, but
maybe I did the numbers wrong.
Yeah, but the thing is that you need somehow to guarantee this simultaneously for all colors, right?
That should be okay. That's just a concentration thing over n and things.
But it's a concentration. But even for 1, wouldn't you need like extra square root n somewhere? Like, so just, I mean, I don't know, is there anything like, so this here, if you would write it just this way, you could have written +5 n to the 1/2, right? And it would still work out for this bound if it was just as simple as that.
Maybe I messed up something with the numbers. So yeah, when you screw, yeah, this would have a half there. Hold on. So what do you potentially want to do?
No.
You want to?
No. Maybe I'm wrong. No. I think I'm doing the multiplication.
Right. If you
yeah,
try
you're right. It's because even when you multiply by one thing without a square, and a square or not, it doesn't matter. If you multiply it even by one term like that, you need 5 n to the 3/4, right? It's just yeah. So the squared is the same as writing 1 minus 4 over n to the 1/4.
Yeah.
And then you need this 5, right?
Oh,
and
yeah. Then it's when you multiply it out.
Then you can easily get still you can get something like n plus square root n log n on the right, and use concentration for getting a union bound. So it's really the whole argument. You're not hiding any details.
No, I'm not hiding anything. It's like, it is really trivial. So just to kind of summarize, like, we did really just black box this result. So if you can prove this result, obviously you improve the bound here as well. And this is the dependence you get. So if you can prove the weak asymptotic with an error term of the form n over f of n, then you get the strong asymptotic with an error term of n over root of f of n. So just to plug in some numbers here, if say you had n minus log n here, if you could improve this Barat-Gaffer-Sarkozy bound to n minus log n, that would be cool by itself. But you don't actually gain that much in this strong asymptotic, because then this is equal to n minus n over, how is it? F of n becomes log n, right? Yeah, log n over n. So that's what the f of n is. And then here you get n plus 3n over the square root of that log n over n. And you get, this is equal to like n plus 3 root n over log n. So even if you could get a really drastic improvement to the weak asymptotic version, the improvement to the strong asymptotic it's never going to be better than root n. Okay, so that's one remark. Another remark is that this kind of sampling trick we used here, it was quite versatile in that it could apply to a bunch of other problems. So one is the non-bipartite version of the Haroni-Berger conjecture. So that's a separate conjecture which was made in particular, say, by Gao, Romer, Duray, one less than Wormold. And this conjecture is exactly the same as the Aharoni-Berger conjecture, except it drops the bipartite assumption, so it applies to non-bipartite graph. It also asks for a +2 instead of a +1. The reason for that is the following construction of a 3-colored graph. So here's this n is 3. Every color has n+1 edges, but there isn't a rainbow matching using every color. So that shows that at least in general, you need an n+2 here. But this is the only example that I'm aware of where you need this +2. So it's possible maybe that for large n, you can have an n+1 here. And what was known about this conjecture? This one was harder to get anywhere. So previously, the only results here had an additional multiplicity assumption on the graph. So rather than just working for all graphs or for all multigraphs, they were all multigraphs with a bounded multiplicity. And here, Gar, Rama, Jure, one less than Wormold proved a strong asymptotic version of the conjecture, whereas Kivesh and Yerpermian proved the weak asymptotic version of the conjecture. And recently with Correia and Sudakov, we got both the strong and the weak asymptotic version without any multiplicity assumption. And the proof of this, it goes similar to the proof strategy I showed you. So first, you prove the weak asymptotic version using some kind of alternating paths argument, and then you just do this argument, which we saw here. Okay, so that's another application. And then there's 2 more applications. So here's 2 problems, one of which Greenblatt's conjecture was recently solved by Correia and Sudakov. But let me show you how both of them work. So in both of these problems, you have a graph which is colored by n colors, and you want a rainbow matching using every color. So this Alspach problem on the top, the coloring is no longer proper. So in that now colors are 2 factors, meaning just disjoint union of cycles. So this, for example, could be an input to this Alspach problem. So n colors, every color is a 2-factor. You can get a rainbow matching using every color. And Greenblatt's problem, now every color, you again a multigraph, but rather than having a proper coloring, every color is a union of complete graphs. So something like this could be an input for Greenblatt's problem. And the conclusion is, again, you have a rainbow matching using every color. But for both of these problems, this sampling trick I showed you works to kind of transform a weak asymptotic version to a strong asymptotic version. And that's another application. So let me end with 2 open problems. So the first one is a different direction in which you can strengthen the Reiser-Brialdian-Stein conjecture, which is you get rid of the proper coloring assumption completely, and all you assume is that every color has the same number of edges. So for example, for n equals to 3, something like this. And here Stein at one point conjectured that this should already imply rainbow matching of size n-1. It turned out to be false. You can get such colorings without rainbow matching of size n minus log n. but it's really intriguing about whether there's some kind of asymptotic version of this is true. So that's one problem I'd love to see solved. Another one is, I think, a very natural candidate in which to use some variant of this sampling trick I showed you. So it's a problem of Wang. You have a simple graph this time, and it's properly colored, and the size of the graph is at least twice the minimum degree. And what you want to find is a rainbow matching using of size the minimum degree. So here, it's known when instead of this 2, I think you have something like 3 maybe, or some number bigger than 2, it's known. And it's also known that if you, instead of the minimum degree here, you have something, the minimum degree minus, I think, delta of G to the 2/3, that's also known. Which you can think of as the weak asymptotic version of this problem. So then it will be natural to somehow get the statement written here, but we couldn't see a way of doing it. So let me stop here for questions.
Great, thanks a lot. Thanks, Alexey. So maybe let's all unmute and clap Alexey. Give him an applause. So any questions? So maybe just a small comment.
Mm-hmm.
Now I don't remember that well, but my feeling is that with Kuhn Ostos and Ji-Hoon Kim, we did something on the Stein's conjecture.
Yeah, sorry, I meant to mention, I forgot. Yeah, what you proved is something like if every color appears little of n times in every row and every column, right?
Yeah, something like locally, yes. Yeah, no vertex has more than n over log n.
Oh yeah, so yeah, appears little o of n times. Was it little o of n? Do you remember?
I think it was n over log n or something like that.
Okay, so that in each at each vertex. Yes, and this is proved by Andre, Kim, Kuhn, and Ostos, I believe.
Okay.
Yes, yeah, that's, and you prove this using some version of the nibble, if I remember correctly, right?
Yeah, nibble plus absorption.
Yeah, and this is a really interesting problem where the nibble doesn't seem to work in the full version of the problem, and it's not clear if it can or it can't. Maybe there's some really clever application of it which doesn't use this this boundedness assumption that you have. So that's something I'd love to see.
Mm-hmm.
That's a great remark.
Great. And any more questions? Well, okay. So if not, thanks a lot, Alexey, for a great talk. Yeah, it was really interesting, and lots of proofs. I think it should be good for the students to learn about this. So yeah, thanks a lot, and hope to see you sometime soon in real life.
Sure. Bye.
Bye.